Hi everyone, this is Mrs. Hanson. This is lesson 2-6, Nonlinear Inequalities, video 2.64 and 2.65. Our learning target for this video will be for students to be able to solve rational inequalities. Alright, so we're looking at a rational inequality. A rational inequality is one where you have a rational function. Again, a rational function is two polynomials divided by each other. And so what we're looking at here is where this function is greater than or equal to 0. We have 3x plus 4 over x plus 2 minus 3. Remember, we have a 1 underneath that. And we want to know where that is greater than or equal to 0. Now, before I do that, I'm going to go ahead and get a common denominator here. So I get 3x plus 4 over x plus 2, and I'm going to multiply the second fraction by x plus 2 on top and bottom so that I get a common denominator. And we have 3x plus 4 over x plus 2 minus 3x minus 6. Technically, this is a negative 3, and when I distribute, I get negative 3x minus 6 all over x plus 2, greater than or equal to 0. And since I have a common denominator here, I can combine my numerators. The 3x's are going to cancel, and 4 minus 6 gives me negative 2 over x plus 2, greater than or equal to 0. Now, if I think about the graph of this function, of this rational function, we have a vertical asymptote at x equals negative 2 because a vertical asymptote is again where the denominator is equal to 0. So if you set your denominator equal to 0, x plus 2 equal to 0, and solve x plus 2 equal to 0, that means that x is going to equal negative 2. And a horizontal asymptote here is going to occur at y equals 0 because our degree on top is 0 and our degree on bottom is 1. We do not have an x coordinate on top. It's x to the 0 power then. And x to the first, since our exponent on bottom is greater than our exponent on top, then we do have a horizontal asymptote, and that's at y equals 0. So, looking at the fact that we have a horizontal asymptote, we do not have an oblique asymptote. And what we can do is we can start looking at graphing this function. One other thing I can do is find the y-intercept. The y-intercept is when I plug in 0 for x. So I get negative 2 divided by 0 plus 2. And when I divide those out, I get negative 2 over 2, which is negative 1. And if we look at the function looking at our x-intercept, I plug in 0 for y and set that fraction equal to 0 and solve for x. And if I multiply both sides by x plus 2 right away, I get 0 equals negative 2, which is not a true statement, which tells us that this function does not have any x-intercepts. This graph will never intersect the x-axis. So on the next slide, I'm going to go ahead and look at the graph of this function and go ahead and solve the inequality. Denominator. Alright, looking at the graph of the function, everything we said that would happen is true. We have a vertical asymptote at x equals negative 2. We have a horizontal asymptote at y equals 0, which is the x-axis. Right? Y equals 0 at every point on the x-axis. So here's y equals 0, our horizontal asymptote. We have a vertical, sorry I didn't draw a very straight line there, but our vertical asymptote is at x equals negative 2. And we said our y-intercept was at negative 1, which is true. Y-intercept. And we also said that this function would never intersect the x-axis, which is also true. There is no zeros or x-intercepts for the function. So, what we're looking at is where this function is greater than or equal to 0. And if you look at the graph of the function, the graph is greater than or equal to 0 when it is above the x-axis or touching the x-axis. Now, because we don't have any zeros in this function, because the graph never intersects the x-axis, the function will never equal 0. However, there is part of the graph that is greater than 0. And that is this piece right in here in the second quadrant. Now, if I want to talk about an interval that describes what I just highlighted here, let me go back here and grab the pen. We need to give an interval for what I just highlighted in red. And that interval going from left to right, so if I trace the graph here, right, would be negative infinity to where our vertical asymptote is, which is at negative 2. Okay, the graph, we had, again, this vertical asymptote here, and this piece in red that I highlighted is going to approach that horizontal asymptote but never intersect it. So, our interval or our solution to this inequality is the function is greater than or equal to 0 when x is in between negative infinity and negative 2. Alright, it's time to check your understanding. Go ahead and graph the rational function x plus 5 over 2x minus 6 greater than or equal to 1. One thing that you want to make sure of is that you get the inequality, you get a 0 on one side of the inequality. So what we're going to want to do is say x plus 5 over 2x minus 6 minus 1 is greater than or equal to 0. And this is the inequality that you're going to want to solve. So go ahead and get a common denominator, combine your fractions, and then go ahead and graph and solve the inequality. You have 4 choices, A, B, C, or D. So go ahead and work this out and then press submit. Okay, so looking at this fraction here, we're going to get a common denominator. So what I'm going to do is I'm going to multiply negative 1 by 2x minus 6 on top. Since there's a 1 underneath that negative 1, I can also multiply that by 2x minus 6. And that's greater than or equal to 0. So what we're going to do is we're going to distribute the negative 1 on top. We get x plus 5 minus 2x plus 6. Again, because this is a negative 1, when I multiply it by negative 6, I get positive 6. And my denominator then is 2x minus 6. So I went ahead and combined both fractions because I have a common denominator of 2x minus 6 once I multiply 1 and 2x minus 6 here for that fraction on the right side. So we have greater than or equal to 0 as our inequality. If I combine like terms in my numerator here, I have negative x plus 11 over 2x minus 6 greater than or equal to 0. Just looking at this function, I know that my vertical asymptote is when my denominator is equal to 0. So if I set 2x minus 6 equal to 0, 2x equals 6, that is x equals 3. We're going to have a vertical asymptote. We are going to have a horizontal asymptote when the degree of the numerator and the degree of the denominator are the same. Because our highest exponent on top is 1 and our highest exponent on bottom is 1, then we divide the lead coefficients to find our horizontal asymptote. So negative 1 over 2 is going to be our horizontal asymptote. And if I'm looking at a y-intercept, our y-intercept is going to be at when x is equal to 0. So I should get 11 over negative 6 as my y-intercept. So that's going to be approximately, I don't know, a little less than 2. Whatever 11 over negative 6 is, it's for sure less than 2 because 6 doesn't go into 11 2 times. So what I'm going to do on the next slide is I'm going to go ahead and graph this function, keeping in mind that our vertical asymptote is at 3, our horizontal asymptote is at negative 1/2. We have a y-intercept at negative 1/2, and I forgot to mention our x-intercept, which is where our numerator is equal to 0. And if you look at our function here on top, we have negative x plus 11. And if we set that equal to 0, that means x equals 11 is our x-intercept. So going ahead and graphing this on the next slide, we will go ahead and solve the inequality. Okay, I've gone ahead here and graphed the function, the very first function here, negative x plus 11 over 2x minus 6, and we're looking for where that graph is greater than or equal to 0. And what I graphed in 2 and 3 are the horizontal asymptote and the vertical asymptote. This Desmos gives a little bit straighter line than me sketching it in on the graph. So I've gone ahead and graphed the vertical and horizontal asymptote on Desmos as well. So looking at, just to verify here, it looks like we crossed the x-axis at 11 like we suspected. And we're graphing the y-intercept close to negative 2, but not quite. So what we're looking at for this function is where is the graph of number 1 greater than or equal to 0. So number 1 is graphed in blue. Again, the purple line is my vertical asymptote, the green line is my horizontal asymptote, and I want to know where this function is greater than or equal to 0. And so if I highlight that on my graph, the blue function is greater than or equal to 0, right, until, let me back that up a little bit, until we reach the x-intercept. Okay? Once I reach that x-intercept, you can see this other part of the graph is below the x-axis, which means the y-coordinate is less than 0 there. So this entire function that I've just highlighted in blue has a y-coordinate that is either greater than or equal to 0. So where does that happen? Well, it happens, this part I've highlighted starts really at the vertical asymptote. Right here at the vertical asymptote. Again, Desmos provides a straighter line than I do, but if you are looking at the vertical asymptote, really what we're saying is the graph starts being greater than or equal to 0 at the asymptote, and since the asymptote is not included in our domain, because the function is discontinuous there, when I write out my solution, I'm not going to include 3 as part of my solution. Again, we cannot use 3 in our domain for that function, so therefore we will use a parenthesis around 3 saying that 3 is not included. And we will be greater than or equal to 0 for all x values all the way up until, again, when I reach the x-intercept, which occurs at 11. And I am going to include 11 because our inequality includes 0. It's greater than or equal to 0. And since at 11 my y-coordinate is 0, I'm going to include 11 in my solution set. So our solution is comma 3, or not comma 3, parenthesis 3, comma 11 with a bracket, and that is the solution to this rational inequality. That would mean that C is your solution to the multiple choice question. Alright, we're going to look at a real-world application here. Carpenter is making tables. The tables have rectangular tops with a perimeter of 20 and an area of at least 24 square feet. We need to write and solve an inequality that can be used to determine the possible lengths of the tables. So looking at a rectangle here, we know that the perimeter is equal to 20 feet. And again, if this is my length, my width, and my width, that means that the perimeter is 2L plus 2W, and I know that's equal to 20 feet. And it says that the area is at least 24 feet, so I know the area needs to be greater than or equal to 24 feet squared, or that the length times the width is greater than or equal to 24. Now, if I solve this perimeter equation for W, so I'm going to solve that equation for W, so I'll subtract 2L, and I get 2W equals 20 minus 2L. And if I divide both sides by 2, I get W equals 10 minus L. Now, the reason why I solved that equation for W is because we ultimately want to know what the possible lengths are of the tables. And in order to do that, I need to get rid of or eliminate the W in our inequality for the area. And so what I'm going to do is I'm going to substitute 10 minus L into that area equation and rewrite it as L times 10 minus L greater than or equal to 24. Or I get 10L minus L squared is greater than or equal to 24 if I distribute. So I'm going to move the 24 over. Actually, I'm going to move these terms to the other side. And I'm going to get 0 is greater than or equal to L squared minus 10L plus 24. Again, I subtracted 10L and added L squared to both sides of the inequality. And basically, we're looking for where that quadratic is less than or equal to 0. So what I'm going to do is I'm going to go ahead and graph that quadratic and solve it like I did in the previous examples. So looking at this quadratic trinomial here, this inequality here, this quadratic trinomial can be factored. We're looking for two numbers that multiply to be positive 24 but add to be negative 10. That would be negative 6 and negative 4. And what that tells me is that when I graph that function, since these are the factors, it tells me that L equals 6 is a 0 of the function, and so is L equals 4. So if I'm looking at the graph of the function here, I know that it crosses at 4 and at 6. And since my lead term has an even exponent and a positive lead coefficient, I know both ends are going up. And I know since my degree is 2, I can only have one turning point. So this is a sketch of the graph of the function. Now, I want to know where this function is less than or equal to 0. I want to know where that quadratic is less than or equal to 0. And that happens right here when the graph is below the x-axis. And I'm going to include the zeros in my solution because the function has a y-coordinate that is equal to 0 right there on the x-axis. So my solution to this inequality is 4, 6. For all lengths, okay, again we're describing L, not X this time. This is our length. And since we want to describe the length, and the graph is below the x-axis or less than or equal to 0 when the length is between 4 and 6. So this is the solution to our problem. The length has to be between 4 and 6, the length of the rectangle, that is. Okay, I'm going to check your understanding here. There's another application problem, this time with gardening. A gardener is marking off rectangular garden plots, and the perimeter of each plot is 36 feet, and the area is at least 80 square feet. Write and solve an inequality that can be used to find the possible lengths of each plot. So you have 4 choices, A, B, C, and D. Go ahead and write out your inequality and solve it for the length. Press submit when you're done. Okay, so looking at a rectangle again, we will go ahead and draw in a rectangle. And again, a rectangle has 2 lengths and 2 widths. This time our perimeter is 36, so 2L plus 2W is for sure going to be 36 feet. And we know that the area, length times width, has to be at least 80 square feet, so greater than or equal to 80. So since, again, I want to solve for length, I need to take my first equation for perimeter and solve that for W. And I know it seems counterintuitive to be solving for W, for the width, when you're ultimately trying to find the length. But again, the purpose behind solving for the width in the first equation is so that we can make a substitution in the second inequality there. In the inequality, rather, not than the equation here. So what we're going to do is we are going to solve for W. We get 2W equals 36 minus 2L, so I subtracted 2L from both sides. And if I divide everything by 2, I get W equals 18 minus L. So that means my inequality right here becomes L times 18 minus L greater than or equal to 80, or 18L minus L squared is greater than or equal to 80. Now, ultimately, I want to solve. I'm running out of room here, so I'm going to go up to the top. Ultimately, I want to get all the terms on the same side. So I'm going to get 0 is greater than or equal to. I'm going to move both of these terms to the other side with the 80. I get L squared minus 18L plus 80. And what you want to do is go ahead and factor this. And if you factor this quadratic, you get L minus 10 and L minus 8. Because negative 10 times negative 8 gives you positive 80. And negative 10 plus negative 8 is negative 18. So when you solve this, just thinking about the graph here, I have, I'm going to have x-intercepts, or L-intercepts for that matter, at 8 and 10. So if I go ahead and erase this graph up here, I'm going to make it a little bit bigger. 2, 4, 6, 8, and 10. You're going to cross at 8 and 10. Again, if you set L minus 10 equal to 0, you would get 10, and L minus 8 equal to 0 would give you L equals 8. This is L equals 10. And since our lead term here, L squared, has a even exponent and a positive lead coefficient, both ends are pointed up. And we will have one turning point because our number of turning points is always one less than our degree. Now you could always go ahead and graph this quadratic trinomial, and it will give you the exact same graph I got, probably a little nicer. And what we're looking for here ultimately, though, is our inequality, and then our solutions. And our solutions are from 8 to 10, any length from 8 to 10, including 8 and including 10. And then our inequality, again, was L times 18 minus L is greater than or equal to 80. So if you're looking at the choices here, L times 18 minus L is greater than or equal to 80. You only have two choices for that, B and D. B and D are the only correct inequalities, and then after the semicolon is the solution, and for D they're saying the length should be between 4 and 5, which is not true. We decided up here based on the graph is less than or equal to 0 when the function is between 8 and 10. So our solution here is B, and we are ready to move on.